Most organizations rely on API logs, dashboards, and token tracking to watch their AI operate. They believe they have built governance. But these systems are entirely advisory. They provide post hoc telemetry, meaning they only register an anomaly after a state mutation, a permanent change to the system's data or infrastructure, has already occurred. This creates a latency window. This is the exact duration between the moment an AI executes an unauthorized action and the moment a human receives the alert. In high-speed agentic workflows, where models continuously make decisions and trigger subsequent actions, this latency window allows damage to compound rapidly before intervention is possible. This diagram illustrates the flaw in architecture A. Telemetry only identifies the damage after the mutation has passed the boundary. Watching an AI is not the same as governing it. Observability without deterministic constraint is simply documented liability. The regulatory landscape is moving from theoretical guidelines to operational mandates. Look at this document from the Treasury. The Financial Services AI Risk Management Framework introduces 230 explicit, auditable control objectives. It demands continuous runtime evidence to satisfy them. This graphic shows the breakdown of the legacy SR 11-7 framework. Its guidelines relied heavily on static model assumptions and periodic validation. Agentic systems actively change their behavior between those validation cycles, violating the core assumptions of the old framework. Examiners now expect organizations to cryptographically prove that a specific control was active at the exact millisecond a model executed an action. Standard policy documentation stored in a shared drive cannot satisfy these audits. Regulators require mechanical proof of active constraints. Look at this text from Section 611702 of the Colorado AI Act. It introduces a demanding standard, requiring developers and deployers of high-risk AI to use reasonable care to protect consumers. During an enforcement action, post hoc monitoring structurally fails this test of reasonable care. It inherently accepts preventable harm as a standard operating condition while waiting for an alert. Allowing an AI system to finalize a consequential decision, like denying a financial service or filtering a housing applicant, before governance can intervene, carries severe legal liability. To satisfy an affirmative obligation of care, governance must move directly into the execution path. It must intercept and evaluate the AI's intent before any state mutation occurs. This architecture diagram shows the required division. When the law requires harm prevention, enterprise systems must shift from the advisory policies of Architecture A to the hard deterministic execution boundaries of Architecture B. Governing non-deterministic intelligence begins with a strict engineering axiom. Intelligence must be structurally and physically severed from execution capability. AI models and agents must be treated exclusively as untrusted compute nodes. This diagram of hardware-isolated enclaves shows the agent contained within a micro-VM. A micro-VM is a lightweight virtual machine that provides strict, hardware-level isolation for individual tasks. The execution substrate must be physically stripped of specific networking primitives. The agent cannot have access to DNS resolution, the system that translates domain names to IP addresses, or outbound TCP stacks, the protocols required to establish external internet connections. It also cannot access raw sockets. This is a stark difference from attempting to restrict capabilities through LLM system prompts. The capabilities are completely removed at the hypervisor level. If an AI retains implicit routing capabilities and can route itself to external infrastructure, it cannot be governed. True isolation is a physical hardware constraint, not a logical policy decision. It eliminates all implicit execution pathways. Without direct tool access, execution requires a new mechanism. The system uses an RPC stub model. An RPC stub is an internal endpoint that receives a request and forwards it to a separate control system. As shown in this schematic, the agent submits a structured intent payload to the RPC stub, rather than executing the action directly. The RPC stubs then forward these payloads exclusively to the runtime governance control plane. This triggers the pre-execution authority gate. This is a deterministic checkpoint where the intended state mutation is rigidly inspected against established rules. To ensure sub-millisecond evaluation latency at runtime, high-level human policies are compiled into low-level attribute-based access control, or ABAC, rules. These rules grant permissions based strictly on verified user and environment characteristics. The gate operates on a strict fail-closed default mechanic. Any ambiguity in the intent, or lack of explicit permission in the policy, results in an immediate execution halt. This architecture strips probabilistic reasoning from the enforcement layer. Execution depends entirely on explicitly verified authority. When the control plane detects an unauthorized egress or a state mutation attempt, the mechanical consequence is immediate. At the hypervisor boundary, the system executes instant packet drops and total suspension of the execution thread. The agent's memory state is completely frozen. It cannot autonomously retry the blocked request or attempt an escalation path. Simultaneously, the system automatically generates substrate-level egress rejection records, permanently bound to the specific policy version that triggered the halt. Deterministic enforcement is highly observable. The unauthorized transmission never physically occurs, which turns a blocked event into positive audit proof. Single transaction enforcement is necessary, but it has a critical limitation when deployed over long autonomous timelines. Catastrophic failure rarely happens in one step. It occurs through the slow accumulation of permitted actions. This chart represents behavioral drift. Over time, an agent's frequency increases, its scope expands, and its context drifts until a series of safe actions evolves into systemic deviation. To counter this, the architecture includes a drift guard layer. This operates as a parallel enforcement loop alongside the authority gate. The drift guard maintains stateful behavioral context across multiple distinct requests and sessions. When velocity or semantic thresholds are breached, the system executes an automated suspension of all privileges. The intervention is captured as a structured enforcement record, tying the halt to the behavioral state. To prevent irreversible systemic deviation, governance must constrain an agent's overall trajectory across time, not just gate its isolated decisions. External examiners bring a final paramount requirement to AI deployments: non-repudiation and cryptographic proof of enforcement. This flowchart shows the immutable receipt service. Notice how receipt generation is located directly within the synchronous transaction loop. These receipts cryptographically bind policy versions to state mutations. The system has an absolute dependency on attestation before a final commit occurs. This acts as a strict failsafe. If a receipt cannot be synchronously written to the ledger, the entire transaction is automatically rolled back. This mechanism creates a hash-chained, tamper-evident audit log that perfectly satisfies regulatory examination. Enterprise AI fails because execution runs unconstrained. If governance is not deterministically enforced before state mutation, it isn't governance. It is hope.